This is one of my favorite sequences of numbers. It's a kind of silly and playful sequence, but it has all sorts of really beautiful mathematics behind it, as well as some less beautiful math like solving this ugly degree 71 polynomial, but don't worry, we'll let the computer handle that. But before I tell you about the sequence, I want to say that we just passed 500,000 subscribers on this channel, which is just kind of mind-boggling to me. My core belief is that math is for everybody. It's part of why I'm doing this channel. So whether you've been watching videos because of a math course that you have to take, or just to see all the interesting math that's here for fun, well, just thank you for engaging with mathematics. And a particular thank you to all my Patreon and YouTube members. You guys are all amazing and make it so much easier to be able to do what I do here on YouTube. So how does this sequence work? I want to start with the number 3. And if I read this with repetitions, I'd say I've got a single 3 or maybe 1 3. Well, then the next term is 1 3. You write down precisely how you would say it. Okay, 1 3. That consists of 1 1 and 1 3, so that's my next term, 1 1 1 3. This one has 3 ones in a row and then 1 3. I'm counting with repetition here. So what do I write down? 3 1 1 3. This is sometimes called the look and say sequence. You just write down the way that you would say it. Then it's 1 3, 2 1s, and 1 3, and I can just keep on going, getting term after term after term, where I look at the previous one, and then I say out loud how many 1s and 2s and 3s there are. Now this sequence grows quickly. Like if I go out to only the 50th term, well, the 50th term has almost 1,000,000 digits in it. This vaguely looks exponential to me, so maybe I'm going to try to take logarithms, and if I plot the logarithm of the number of digits in it, well, now what you get is something approaching a straight line. But why? And what does the slope of that line represent? So let's try and discover a few properties. This time I'm going to start with the sequence 2 3, a different initial seed. If I evolve that, I get 1 2 and 1 3. And if I evolve that, I get 1 1 and 1 2, and then 1 1 and 1 3. And what I notice about the first 3 terms of this sequence here is I can kind of divide them in half. The left and right subsequences, they're actually evolving separately from each other. If I keep on doing this term after term, it always has this property. The left term evolves and the right term evolves, but they don't cross over that center dividing line. They just don't interact at all. And the reason in this particular case is, well, if I color code the end of the left sequences, it always ends in a 2. If I color code the start of the right sequences, it has this pattern, 1 3 1 1 3 1, 1 3 1 1 3 1. It always starts with that cycling pattern of 1s and 3s. If they had ever aligned and were the same digit, like a 2 on the left and the right, then those would be combined, the left and the right side interacts. But here it's separate.
As you evolve these strings over and over again, they keep separating into combinations of these smaller substrings that then evolve entirely separately without interacting with the substrings beside them.
Now, I encourage you to pause and play around and try to think about all of the different ways that you can have these splittings that divides these long sequences up into these smaller chunks. But I'll spoil the answer for it. It turns out that there is a list of 92 different subsequences. And all of the things on this list have this sort of atomic property that one of the subsequences evolves into one or more of the other ones on the list. For example, right at the top, the 92nd entry on my list, well, it's the subsequence we started with, the subsequence just 3. If you evolve it, you would get to 1 3, and I've listed that as the 91st entry on my listing. So the 92nd turned into the 91st, the 1 3 turns into 1 1 1 3, that's going to be the 90th. I'm going to order them in this sort of sensible way. And as I carry on, they each evolve into the next one down on the list until I get to this 82nd subsequence on the list. And here it says it evolves into the 85th as well as the 67th. Like, okay, here's that term. This is the one I called the 86th. And when it evolves, it becomes not just a single subsequence from the list, but actually stuck together 2 of the other ones, the 85th and the 67th together. So that's possible. And if I go all the way down the list to the very bottom of it, you get all the way to the first sequence, which is the sequence 2 2. And 2 2 is a really interesting one because if you have 2 2, you would say there's 2 2s, which is itself. And then you'd evolve that and you'd get 2 2s and then 2 2s. So the sequence 2-2 evolves into itself over and over and over again. Conway, who is the guy who kind of popularized this sequence, although it was originally shared with him by one of his students, actually thought that the sort of atomic nature meant that we should just call these like elements from the periodic table. So he would call this first sequence hydrogen, and the 92nd one he'd call it uranium, and you kind of imagine that uranium is decaying down into all of these other elements on a sort of mathematical periodic table. This is all a little easier to see graphically. Here we have 92 vertices. We always have the nth vertex evolves into the n-1th vertex. That's how we ordered these. So you get that backbone of this spiral from 92 all the way down to 1 in the middle. But there is also a bunch of branching going on. It isn't just a spiral. So let's watch. If we start at the 92nd vertex, you go down to the 91st, the 90th, and so on, all the way down to the first branching, which happens at the 86th vertex. So now our string consists of the 85th and the 67th. Now both of those substrings keep on spiraling down, and over time they keep branching out again, and our string is getting longer and longer, and I'm using redder colors to represent substrings that are repeated more and more times until every single substring is hit at least once, probably many times in a very long subsequence. I can also use a bar chart to represent the frequencies of the different substrings. The height now represents the percentage that a particular substring has, and I'll start with a uniform distribution. Like, let's imagine our substring consists of one of every single one of the different 92 substrings. And as we evolve over time, you'll notice that some of the elements become more common, some of the elements become less common. The most common of them all is the first substring, that 2-2. And this is because of that spiraling, everything spiraling down to 1. And so over time, about 10% of the substrings are going to be the first one. But every single one of the 92 substrings actually is represented, even if it's just small amounts, as you evolve in time. But this immediately leads to another big question, like, why this distribution? Like, what's going on there? Now, the big theorem here is called the Cosmological theorem. And it says that these 92 elements are not just ones I've discovered that have this behavior, that no matter how you start with your string, it's going to eventually evolve into combinations of those 92 elements. Now, it's kind of fun, the lore of this theorem. It was originally proven by Conway, except that proof is kind of lost to us. Like, he wrote in an article once that he spent a month working out hundreds of cases by hand to prove that this theorem was always true. Those pieces of paper, they're lost in history. However, we actually have had a number of people who have gone and proven this theorem since then, so we can be quite confident. Don't just have to trust John Conway's word for it, although I would have. So, while we're not going to prove this theorem, I want to show you the mathematics about how we can get to this growth rate, how we can understand this distribution. And to do that, I'm going to translate from this graph that we've seen, this directive graph, to this matrix. Sorry, it's a 92 by 92 matrix because there's 92 vertices, so I'm sure you can barely read it. But how does it work? I mean, if I zoom in onto sort of the top corner, it looks something like this. Basically, the idea is if in your graph you have an edge from one vertex to another, you put a 1 into this matrix at the right spot. And if you don't have an edge, you put a 0. So like, for example, this location here, this is the 3-2 location, third row, second column. And it's going to be a 1 because the second vertex evolves into the third vertex, as well as several other things. You'll notice there's this big diagonal. It's actually not the main diagonal. It shifted 1 off. That was the basic pattern that the nth vertex always went down to the n-1 vertex. And actually, it's not just zeros and ones. There's 1, 2 there. And that's just because one of the subsequences evolves into 2 copies of one of the other subsequences. So let me show you how to use this matrix to actually do calculations. So imagine I have a string like this one, 2, 2, 2, 2, and then the long subsequence that represents the third one on our list. So I'm going to represent this string with a vector. This is the vector, which is 2, 0, 1, 0, and then zeros after that. So the way I want you to think about this is that the 2 in the first location represents the fact that the first subsequence, the number 1 subsequence, is represented twice. And then the 1 in the third location represents the fact that the third subsequence is represented once. So instead of having to write out an entire string, I can just write down one of these vectors to represent my string. And then I can talk about the length of it. Length being the number of bits. That's what I'd be interested in. So to figure out the length of the string, then I have this sort of weird notion of a length of a vector. We have lots of notions of lengths of vectors in linear algebra, but this one is scaled by the lengths of the substrings themselves. So because I have 2 copies of the first string, I should have 2 times the length of the first string. And then I have 1 copy of the third string, so 1 times the length of the third string. What were those? Well, the length of the first string was just 2. 2 has length 2. And the length of the third string, if you count it out, has 27. So you add all that together, the length of my entire string is 31. So given a string, you get a vector, and then you can use this weird notion of length to figure out the number of digits inside of your string. And what I like about vectors is I can take a vector and I can multiply it by a number. Let's multiply by, say, lambda here. If I do that, then I have a real nice formula for what the length of this new vector lambda times v is. That just goes in, and it puts a multiplicative factor on every single one of the components. Well, what do? You just multiply the different lengths all by this lambda, which is the same thing as just lambda times the length of the vector. So if I have a vector and I multiply it by a scalar, the effect on lengths is just multiplying by that scalar. That's going to be very nice for us. Okay, so we've seen vectors and matrices. Now let's put them together. So here is the matrix. I will call it T. I am going to apply that matrix to a particular vector, which is going to be V. So in this example, maybe I'm going to start with a string that only consists of 1 copy of the second string. So 0, 1, 0, and so on. I then can do matrix multiplication. This is going to give me, in this case, the vector 1, 0, 1, and so forth. And just represented the fact that the second string evolved into the first and the third, and maybe more things inside of the dot, dot, dot. Like, remember from our table, the second subsequence, it was going to evolve into the first and the third, and so on. So behind the scenes, when I was animating this picture of this directed graph and everything was moving around, all I'm really doing is taking vectors and multiplying them by matrices. That's what's happening behind the scenes. Now, perhaps the most powerful tool in matrices is eigenvalues and eigenvectors. So an eigenvalue-eigenvector pair is a combination of a number and a vector. And the idea is T is a big matrix, right? 92 by 92. It does all sorts of complicated stuff to most vectors. But for some very special vectors, it's just stretching. Some very special vectors, you take this whole 92 by 92 matrix V, you multiply it against the V, and you just get a stretching factor of lambda times V. That's an eigenvalue-eigenvector pair. And it's also really nice because you can do this over and over again, right? Like we're iterating many, many times. So I can take this matrix T to the power of n, and I can evolve n times. What do I get? I just stick out the value of the eigenvalue n times if I'm going in the direction of an eigenvector. Now, how do you find eigenvalues, eigenvectors? Well, I'm just going to link down to my linear algebra playlist for that. You can check out all of the details there. But if you've seen those before, you'll know that you have to come up with something called a characteristic polynomial. And this is the 92 by 92 matrix. I don't want to do that. So I'm going to turn to the computer. And this is the resulting characteristic polynomial that you get. It is this monstrosity. It's a degree 92 polynomial. It equals 0, and I'm trying to figure out the x values. The x values I get out of this, those are going to be my eigenvalues. There's a little bit of factoring at the beginning. There's x to the 18. That's the 0 eigenvector. It's x equal to plus 1, x equal to minus 1. But after that, I get this really messy degree 71 polynomial appearing. So our eigenvalues are the roots of this polynomial, and okay, again, we can use the computer to help us out. This is all 71 roots of them, and oh, aren't they pretty? This is the complex plane, so many of the roots have an imaginary component. You get this nice symmetry here, but notice this yellow one. There's one there which is positive. It's sitting on the real axis, and it is larger than all the others, larger in terms of the distance from 0. There is a largest real eigenvalue. This eigenvalue has a value of about 1.3036 and so forth. And I can also use the computer to spit out the corresponding eigenvector, which is all of this mess. And okay, that looks probably pretty messy, but hold on. Those numbers, do you see how in the first component it's about 9? Remember our distribution chart where the first component was about 9%? This distribution chart that you see here, the heights of that distribution chart are just this particular eigenvector's values. That's really interesting. So why is that true? So now I want to imagine that I have a list of eigenvalues, lambda 1 down to lambda m. Indeed, that was all the different roots to that big characteristic polynomial we just saw. And for simplicity, let's assume there's one eigenvector for every one of these different eigenvalues, v1 down to vm. Now, if I start with some particular string w, a string that's represented by a vector w, then I can ask, can I write it out as a linear combination? Can I write it out in terms of all of these different eigenvectors? And if I can, I have a really lovely property that comes out. Watch this. I'm taking this matrix t to the n and applying it to this thing. I want to evolve my w these n times. But applying t to the n to the eigenvectors, as we know, behaves really nicely. That's just the stretching factors of lambda 1 to the n all the way to lambda m to the n. And I can look at these particular terms, and if I have one that is largest, I may as well put it first. Let's say that lambda 1 is the largest of them. I can factor that one out. So I'll write this as lambda 1 to the n, and then all the other terms have all the other lambda i's, but divided out by lambda 1. That's what happens if I factor them out. And now we're going to imagine that we evolve and evolve and evolve a lot. Our n is getting really large. So this ratio of these eigenvalues, this is going to 0. So what do I get? I get two things. I get this lambda 1 to the n, this growth rate, this exponential growth rate with this particular value of lambda, we saw 1.3 or so. And then it gets multiplied by this c1 v1. It's not the original w. It's just the portion of that w that's in this v1 direction. But then that stretching factor doesn't multiply the original w, it multiplies the first eigenvector. So this is why over time the distribution that we got just looked like that first eigenvector. As we see, the approximation here is it becomes multiples of that first eigenvector. Now, this does depend a little bit on your starting w. Like if I started with the empty string, that would be a w of all zeros. Your c1 would be 0 here. Likewise, if I started with the string 2, 2, remember 2, 2 evolves into 2, 2, and then 2, 2, and 2, 2, and so forth. In that particular case as well, the c1 would be 0. But the cosmological theorem actually implies that for everything else, the c1 is non-zero here, and so you get this kind of behavior. The people who know a little bit more linear algebra in the room will notice I've left out a few different details. This is technically not a diagonal matrix. It's got a Jordan canonical form because of that x to the 18th term, but you can check that the basic limiting argument works in this particular case. And so ultimately, by taking this matrix, figuring out its largest eigenvalue and its corresponding eigenvector, you get the growth rate in the lengths of these strings, and you get the ultimate distribution. It's this eigenvector. Now, if you want to get better at math, then I strongly recommend the sponsor of today's video, which is Brilliant.org. Brilliant is an online learning platform that helps you achieve your learning goals in math, science, and computer science. It has 3 components that I really appreciate. Firstly, Brilliant is really interactive. You get to actually play with the animations, you get to write and execute your own code, you get to make predictions about what you think will happen. Secondly, I appreciate that Brilliant really focuses on understanding why things are true and not just telling you what is true. It really helps to build your intuition that lays the background for deeper understanding. And finally, as a professor, I really like how Brilliant is constantly peppering you with questions to make sure that you are really understanding the content and you leave no stone unturned. This helps you self-regulate your own learning and ultimately make big strides towards your learning goals over time. To try everything that Brilliant has for free, go to brilliant.org/Trevor Bassett or click the link down in the description to get an additional 20% off an annual premium subscription. With that said and done, if you have any questions about this video, please leave them down in the comments and we'll do some more math in the next video.